So let's talk about motion with constant acceleration. So this is definitely a special case. Most motion does not have constant acceleration, right? When you step on the gas pedal in your car, or you step on the brake, or you start running, or you slow down on your bicycle, or whatever you're doing, typically that motion is not constant acceleration. It's some kind of acceleration which is changing with time. But turns out there are special cases when acceleration is constant, and we can take those special cases and solve problems using equations which apply only to those special cases. So these equations that we're going to derive in this video apply only to the special case of constant acceleration. So you may ask, why are we coming up with these unique equations? Well, it turns out that this constant acceleration motion is common in nature. Any object moving under only the influence of gravity near the surface of the Earth experiences constant acceleration. Right? So if I drop an object, it's going to accelerate at a constant rate as it falls. Right? Same thing with this basketball that we saw in a previous video from Flipping Physics. Right? If I start this ball on this ramp and let it just roll, it's going to roll down the ramp. It's going to speed up the entire time, but the amount it's speeding up is going to be constant. Right? So if I plot the acceleration vector, I get this yellow vector here. It's a constant at all times. So the rate of change of velocity is a constant. The velocity is increasing at a constant rate. Right? So at this moment it's moving, say, 2 meters per second. At this moment it's moving 4 meters per second. At this moment it's moving 6 meters per second. At this moment it's moving 8 meters per second. Right? Every second it's moving 2 meters per second faster. Right? So it's accelerating at a constant rate. So this is a special case, and a lot of motion in the world around us can be described using these equations that we will now derive. So let's do that. We are given just this one fact: acceleration is a constant. And our goal is to derive 4 separate equations which are true only in this special case of constant acceleration. Okay, so when we use these equations, we have to recognize that they're not going to apply to every single problem. They're only going to apply to problems where we know that there is constant acceleration. Either it's going to say explicitly in the problem something moves with constant acceleration, or we are going to be able to use our physics conceptual knowledge to know that there's constant acceleration. For example, if I throw a ball up into the air, I know that throughout its motion it's experiencing constant acceleration due to gravity. Right? So that will tell me, okay, I can apply these 4 equations. But let's go ahead and derive them. So first of all, we have an equation that we've shown previously. Our relationship between velocity and acceleration is with this integral relationship, right? So I want to know my change in my velocity, right? This is my initial velocity, this is my final velocity. So if I have some initial velocity, how does it change to become my final velocity if I'm accelerating? Well, what I have to do is I have to integrate the acceleration as a function of time. And if acceleration is a constant, well, it's easy to integrate a constant. I just get acceleration times time. And so I get this nice simple equation. My initial velocity plus acceleration times time is equal to my final velocity. Right? So this is just a good conceptual understanding of what acceleration is. Right? Acceleration is how our velocity is changing. And the longer I apply that acceleration for, the more my velocity is going to change. Okay? So that's our first useful equation. For our second equation, we can now use our integral equation that relates how far we traveled, right? This is our initial position, this is our final position, as a function of velocity, right? If I know my velocity as a function of time, I can integrate that, and that'll tell me my change in position. So I can plug in this equation for velocity into here. If I do so here, I can now integrate this. Integral of my initial velocity is just a number, it's a constant. So this just becomes initial velocity times time. Acceleration is a constant, so this integral just becomes 1/2 acceleration times time squared. And I get this very useful equation. So if I know my initial position, my position at time equals 0, and I travel, say, 60 miles per hour at a constant rate, well, my acceleration is 0, my initial velocity is 60 miles per hour, and if I say I do that for an hour, well, if I drive 60 miles per hour for an hour, I drive 60 miles, right? So this becomes 60. Okay, so this part of the equation makes some conceptual sense. And then this part of the equation takes into account the fact that my velocity may be changing. Right? I may have acceleration. So if I have constant acceleration, this part of the equation tells me how far I travel due to that acceleration. Okay, so this will be a very useful equation for us. And I note that, okay, I can solve a lot of problems with these two equations, but what if I don't know the time? If I don't know how long something is flying through the air for, or I don't know how long something is accelerating for? Well, both of these have time in them, so I can't use these equations if I don't know the time. But, okay, maybe I can use these two equations to come up with an equation that doesn't have time in it. So let's try to do that. Let's take this red equation and rearrange it and solve it for time, as I've done so here. And then now let's plug this into our green equation, right? Here for time, and here I'll replace this time squared with this squared. Right, so that's what I've done here. It's pretty ugly looking, but it doesn't have time in it, right? So that may be useful. We'll do some math, multiply this all out, we get a bunch of terms, some of which cancel. That gives us this equation, which we can then rearrange to give us this nice equation, okay? And you'll note this does not involve time. So if you want to know, how the velocity of an object is changing given some acceleration and some displacement, this equation can help you with that. Okay, so that's really nice. And then finally, what if I take this equation in red and I solve it for acceleration and I plug that acceleration into here, right? So I take this equation, plug it into this equation for acceleration, plug it in, and I get this equation, which is ugly, but you'll note it doesn't have acceleration in it. So if I don't know the acceleration, this may be useful. If I factor out this v squared minus v naught squared into this, I note my v minus v naught cancels, and I get this nice equation, which does not have acceleration in it. So that could also be useful to you in solving problems. All right, so now we have these four nice equations that apply when you have constant acceleration, and we can use them to solve problems. Okay, so the next issue is, how do I decide which equation to use? Right, we have these four equations, and if you identify a problem where this is true, constant acceleration, once you identify this, write down all four of these equations on next to that problem, because it's really likely one of these will be useful to you. Okay, but now we have to figure out which one will be useful. So in doing that, in solving a problem, the next thing I would do is read the problem and write down all of your knowns and unknowns, right? You may know your initial velocity, you may know your final velocity, but not know your acceleration or something like that, right? So write down what you know, write down what you don't know. List them out explicitly. Some of them will be told to you in the problem. Some of them you may just know. For example, you may know that the acceleration is equal to the acceleration due to gravity or something like that. Okay. Once you know all your knowns and unknowns, you can look at these equations and try to find the equation that has one unknown and everything else known, right? Then you can use that equation to plug in all your knowns and solve for your one unknown, right? So that's our goal. Take some practice, but hopefully you get some experience with that in the homework, and we'll do a lot of practice problems in video also. Right, so our first equation here depends on final velocity, initial velocity, acceleration, and time, but it does not depend on position, right? So if I have three of these known and one unknown, I can use this equation to solve for that one unknown. This equation depends on our final velocity, our initial velocity, our acceleration, and our displacement, or our final position minus our initial position. It does not depend on time, right? So if I have one of these unknown and everything else is known, I should use this equation. Our orange equation here, again, depends on our displacement, depends on our initial and final velocity and time. It does not depend on acceleration. So if one of these is unknown and everything else is known, I use this equation. And finally, your green equation does not depend on our final velocity. So if I know how fast I'm moving initially, I know my acceleration, I know how long I'm traveling for, I know where I'm starting, this will tell me where I finish, what my final position is, right? And I don't need to know how fast I'm traveling at that final time, okay? In some cases, you may use a combination of these equations. In some cases, you may want to find some intermediate, make one of your unknowns, even if it's not asked in the problem explicitly, but if there's one of your unknowns that you can figure out with these equations, that may be helpful to you in solving for the unknown that you actually need to get the answer to the problem. Okay, so hopefully we get some practice with this, and don't hesitate to ask me questions on them. Thank you.